So we learn what is called as so I was talking about three things yesterday, right? I mean, when you fit the model, one of the three things will happen, right? One is model will underfit. Two is just right fit. And three is overfit. One of the three things will happen. So in case of classification problem, right, this could be example of, no, this is not a right example. Actually, let's say these are data, and if you fit a line, this is an example of underfitting. No matter how hard you try, line just does not have enough capacity to fit the circular decision boundary. Okay. Again, just right fit. Just right fit, correct? You are able to find a decision boundary such that you are able to separate one class from the other in this case. Okay. And let's look at the third case, which is overfitting. Let's say your data something like this. So you create a decision boundary which is something like this. Unnecessarily wiggly decision boundary, right? You can get this by fitting higher order polynomial. You can use higher order polynomial and train the model. You are likely to encounter such a boundary. So this is overfitting. So do you know remedies for each of them? Let's talk about it. So whenever your model is underfitting, what is the problem of the model that underfits? It does not have enough capacity. So how do you address that problem? By increasing the capacity, by adding more features. One of the ways was adding polynomial features. This is the remedy. Don't say that add more data. If you add more data, if you don't have any capacity, then you are not able to come out of underfitting. This is one of the standard questions we ask to check the level of expertise of the data scientist. If your model is underfitting, what will you do? Some people say that add more data. Not a correct answer. Even after adding more data, it's not going to be useful because model just does not have enough capacity. Okay. Just try it, you don't have to do anything, just accept the model, proceed with evaluation. And here, this is classic overfitting case. I was telling you yesterday, right? You just prepared for the questions that were there in the question bank, and you don't know anything beyond that, right? So in some sense, model is not generalizing. Model is not learning the general concept, right? So model works very well on the training set, but on the test set, it doesn't perform as well. So how do you fix overfitting? One way of fixing overfitting is to get more data. Okay. And second is no problem. I'll insist. Get more data is one thing. And second is you want to penalize the complexity. Second is penalize complexity. Penalize the complexity. We'll see how to penalize the complexity. Right? Huh? Yeah, simpler model, you can try simpler model or you can penalize complexity. If you don't want to, let's say, use other model, same model, you can penalize the complexity. We'll see that. Underfitting could also happen if you penalize too much. Okay. So one way of fixing underfitting is also reduce penalty. But you have not seen, right? What is penalty, how it is applied and other things. We'll see that now. Is this clear? Do you see these problems? So now let's try to figure out what is a penalty. So penalty has to go in loss function, right? Because loss function is what helps us find out the parameters, right? We optimize our loss function to find out right set of parameters. So if we add penalty in loss function, that will help us address the complexity issues. So let us write it down. So what was our penalty for logistic regression? And by the way, this is universally applicable for all machine learning algorithms. So take linear regression, take neural networks, take any other SVM. This particular thing applies everywhere. So you take a loss function. What is a loss function for us? Say loudly. Okay, what is it called? BCE. First, we always write it in simpler way, without any equations, right? So you have BCE loss. So now you add penalty. You want to penalize this, right? So you want to minimize BCE loss. So you want to add a penalty. So it will have motivation to reduce this penalty. So this lambda I'm adding, this is, let me not even put any symbol. So some penalty, right? And we weigh this penalty with this lambda. This is called as regularization rate. Got it? So how can we define penalty? So there are multiple ways of defining penalties. One way is to sum of the weights. We have weight vector, correct? So let's say if you have a weight vector W with, let's say, two components, 10 and 20. So this is a vector, correct? So you can find the second norm of the vector. You can use either the second norm of the vector or the first norm of the vector. So how do you calculate this? This is calculated as in this case, this will be sum of, there are two weights, right? W1 and W2. So W1 square plus W2 square. This is the penalty. This becomes the penalty in second norm. So generally you can write this as sum over J, Wj. J goes from 1 to M. We usually do not include bias in penalty term. Bias is not included in the penalty term. Remember that. Okay. Square. second norm. So this is called ridge regularization. This is also called Tikhonov regularization or L2 regularization. Getting it? Alternatively, you can use first norm, which is sum of absolute values of weights. Sum of absolute values of weights. So more generally, you can write this as J goes from 1 to M summation. Okay, so this is called lasso or L1 regularization. Clear? So this gets added here. So because of that, your gradient will also change. Now you know simple way of calculating gradient without doing any mathematical magic using grad function in JAX. So you can use that by specifying this as your loss function. Yes. Okay, good question. We'll see that. So the question is, when do we use lasso and when do we use ridge regularization? Okay. Are there any participants online? Okay. All right. So let me quickly write the equation. Minus 1 by n, I1 to n, yi log yi hat plus 1 minus yi log of 1 minus yi hat. These are non-regularized loss. It is BCE loss. Now BCE with L2 penalty is JW plus lambda times sum over WJ squared. Correct? And got it? Now, if you look at this L2 regularization, so this typically looks something like this. It is circular. Okay, is a shape. So what happens is that if you believe all your features are important for prediction problem and you don't want to lose out on any of the feature, go for L2 regularization. If you believe all your features are important for prediction go for L2 regularization. So the effect of this would be that this doesn't allow any weight to take arbitrary large value and do overfitting. So it has got incentive to keep values of this WI small enough. So ridge regularization gets us the weight values which are small. Okay, but all weights are considered. Whereas if you believe that some of your features are not useful, there are some unwanted features, then you go for lasso or L1 regularization. So L1, the way it looks is L1 is diamond shape. This typical contour of L1 regularization. It's diamond shape. So it has tendency. So what it will do is, in order to minimize this lasso, what it will do is it will push some unwanted features to 0. Right? It will make them 0, and only important features will have non-zero weights. Getting it? So L1, you can think of L1 as a modern way of doing feature selection. Right? So yesterday you were asking how much, what degree of polynomial we should be including and other things. So one way, if you have enough compute, you can put in a large polynomial degree function and throw in L1 regularization, add L1 regularization to it. Okay. So you get a very high capacity function with some penalty added. So the effect of that would be that some useless features will be pruned, they will be driven to 0, and only useful features will be retained. So that is one way of solving the problem. If you don't want to do a lot of trial and error, just throw in enough degree polynomial, let's say degree 4 or degree 5, and throw in L1. Okay. So let's look at the demo. I mean, the visual. Let's look at it visually. So now what we'll do is we'll add some noise like this. Okay, we have added some noise. So because of this noise addition, what has happened is some points have crossed over. Now we'll have second order polynomial. And let us not add any noise to begin with. And let's use second order polynomial with L2 regularization with a very small regularization rate. I selected L2 as regularization with regularization rate of 0.01. Now we'll run it. Okay, this is probably okay. This worked. Fine. Now look at the weights. See, the weight is very small here. Correct? Look at the weight over here. And only two major features are getting some weight. If I remove regularization and retrain the model, see what happens. Yeah, the weights are slightly larger in magnitude here compared to the earlier one, right? Look at this point. This is 67, some 67, right? Just check out what weights you are getting. And now I will introduce L1 regularization, some small penalty. This might be too large. Okay, so we got a model. Look at the losses. Are you following? Do it on your laptop. You'll be able to see. You will see that this weight is 0. These two features are not useful at all. So, their weights are now 0. And only these two features are getting some weight. But that weight is also reduced. It is not 0.33 as last time. It is reduced slightly. Yes, some question online. Somebody made some comment. Any questions? Yes. So throw in all the features. Throw in all the features and throw L1 regularization. So model will figure out. Okay, model will figure out which features are important and only important features will be retained. Okay, sounds like magical. How the model will figure out? Good question. We have this loss function, right? And because of this loss function, in order to minimize the loss, what should happen? Simply minimizing this won't be enough. Correct? I need to also make sure that the second part is also minimized. And how will you minimize the second part? Only by including the features which are important. Rest others will be driven to zero. So you want to know the algorithmic details of this, right? Yeah, so you can run gradient descent algorithm on this. Right? There are other algorithms also, but gradient descent also works on this. So you can use a grad function on this and run the algorithm. But intuitively, this is what is happening. I'll try to explain that. What is happening? It's a good question. So let's say this is our data set. Okay. And let's say, now I'm going to do something which is not explained, but I'll try. And let's say these are some of the contours. Of the data. Oh no, these are not W1, W. So these are not X1, X2. These are basically your weights, W1 and W2. Okay. And with ridge regression, we said that ridge regression looks something like this, right? So because of this particular shape, only certain features will be selected whenever there is whenever there is an intersection of the distribution of W1 and W2 and the penalty. This is a penalty function. This is L1 penalty. Okay. So now see, if you don't use L1 penalty, W1 and W2 don't have any constraint. They can take any value. And they'll take values such that they minimize the BCE loss. But now we are telling them that just minimizing BCE loss is not enough. We need to also satisfy this constraint. Then if you have studied optimization course, you'll see that only solution that will be feasible is the one where these two functions intersect, right? And that gets us the sparse solution. And by sparseness, I mean only few features will get some weights. The remaining ones will have zero weight. Okay, so this is intuitively happens. Got it? And same thing happens with BC with the L2 loss. L2 loss will have function like this. So because of this constraint in L2 loss, we are able to include more terms, but with smaller weights. Okay. Now let's go back. Does that answer your question? Does that answer your question? Okay. So let's go back to this. Okay. Now use L2. We saw this, right? It's good. Now where this is useful is, let's say you have a very noisy data set like this. Let's take noisy data set. And now if you try to put the second order polynomial Okay, please pay attention. On this particular thing, if we put the second order polynomial, let's run this. Let's not put any regularization. So now I'm not fitting exactly the straight line. I'm fitting slightly curved line. Correct? But if I want to have simpler model with second order features included, all I can do is I can include regularization with some penalty. We got some second order model, but the weights here will be very small. Look at the weights on these lines. Very small weights assigned to these lines. If you use L1, they have gone to 0. These guys have pretty much gone to 0. Getting it? So this is another concept which we wanted to cover, which is regularization. Any questions on this? Online participants, do you have any questions? Yes. Huh? Good question. Thank you. The question is, can there be other norms? Yes. You can use something like L infinite norm, right? You can try other norms here also, but L1 and L2 are most widely used norms. Huh? More rigid algorithm? Yeah, you can think of including other penalties. You will get other algorithm with more stricter penalties, but generally people have found that using L1 and L2 penalties is sufficient. And you will see these penalties used in most of the machine learning algorithms, L1 and L2 penalties. So this is also a foundational concept. Okay. And when you learn Bayesian machine learning, you will also see some very interesting connections of regularization with Bayesian prior distributions. All right. Okay. One part who has question? Yeah, sure. Yeah. Depending on how much time you have, if you are in too much of a hurry, then use L1. But if you have time to do data exploration, feature selection, then you can go that route. But sometimes what happens is, right, those feature selection algorithms, you should have strong faith in those algorithms because they are also doing some kind of optimization. Some term they are trying to optimize, which could be the correlation with the output or some such kind of a thing. If you believe that the correlation is weak, there is no strong correlation, you cannot really figure out very strong features, then it's a good idea to throw in all the features. But never forget to add regularization. Yeah, that is what I would suggest actually. So once in one of my previous jobs, we came up with this philosophy that we will not do feature selection at all. We will throw in enough. I mean, we will basically use very high order polynomials paired with L1 regularization, and that sometimes works.
Okay. There is a question from Zoom.
Yes.
Like, on what basis we decide which features are more important and which are not?
Okay, that's completely different discussion in feature selection space. I think there will be some talks about that later. There are algorithms for doing that. So you can also, by the way, do feature selection by, let's say, training, let's say, logistic regression model, simple logistic regression model, and looking at the weights of each feature, right? The features that get weight around 0 are not so important. Features that are getting strong positive or strong negative weights, they are very important. Then you can remove those features and then again try another loop of logistic regression. I mean, just the one that you know already, you can use that. But there are specialized feature selection techniques that you need to look at. Sorry? Yes. So basically what you're asking is by reducing features initially, will it have same effect as regularization? Yeah, you are basically making model less complex. You are reducing number of parameters in the model. So you are giving lesser flexibility to the model. Yeah, to some extent, there is some effect of that, similar to regularization. What is regularization trying to do? It is trying to remove the reduce the flexibility of the model, right? By constraining certain weights, by constraining the magnitude of the weights in some sense. Yes. Sorry. Graph also becomes. Yeah. If you use higher polynomial degrees and if you do not put in penalty, you will overfit for sure. So for example, if you read standard machine learning books, they give this example always. So let's say you want to fit in some function to this polynomial, right? So 1, 2, 3, 4, 5, 6, 7. There are 7 points here. So if you use 6th order polynomial degree, we literally get line like this. So if you increase the degree of polynomial, you can fit arbitrary functions to an extent that you can also go to an extent where you will just connect dots. But this is clearly a highly overfitting model. This will not be useful, right? Because if I give you training example, which is slightly different than what you see, sorry, the test example is slightly different than training, then your model does not have any hope. Model doesn't work. Model is not able to predict the accurate value. Getting it? So using higher order polynomial makes you more prone to overfitting. Let me say that. If you have large amount of data, you may not even see overfitting, but there are chances that you are likely to overfit. Okay, if you use higher order polynomials, yes. Sorry. Which? Huh. No. L1 doesn't do recursive feature elimination. Recursive feature elimination is algorithm in itself. L1 does something else. Sometimes you might see that results are kind of correlated or matching. But it uses completely different philosophy. It doesn't use this method. Recursive feature elimination, what they do is, there are two methods in that. One is forward selection and backward selection. So you start with a single feature, build a model, and then you add the second feature, third feature, and you keep checking which feature addition results into jump in the accuracy or jump in the metric that you care about. And if there is sufficient jump, then only you admit that particular feature. Otherwise, you discard that feature. Either you build that one by one, or you take all the features and then reduce it one by one. That is forward and backward selection. But this is different. Okay, any other questions? What time is it? 9:15.
From Zoom. So Purushottam says that regression is used for prediction over continuous data, but logistic regression is used for prediction over discrete data. So can we say logistic regression as a regression?
Logistic regression name is quite confusing for many people. It is there for historical reason. So I sometimes think it this way, right? If you look at the equation yesterday, right? I mean, again, I'm making up something. Don't take this. So see, we saw this right yesterday. There is linear combination followed by nonlinear activation, correct? So here, what we are doing in linear combination is very similar to what we do in linear regression. So it's a linear regression followed by logistic model. So they have probably removed that linear word. So there is logistic activation that we use on linear combination. So you can say that output of linear regression, if you pass to logistic function, you get logistic regression in some sense. But we train this end to end. We do not train these two models separately. But remember that, okay, could be a trick question. People might test you in some interviews or some exams. What is logistic regression? Is it a regression model or classification model? Okay, any other questions?
The question is like, what is the difference between logistic regression and artificial neural networks?
I wanted to avoid that, but looks like, anyways, I'll do that. Not avoiding for, I was trying to avoid it for the sake of keeping things simple. But let's talk about it in a minute. So see, what happens is, let's say these are two features that we have. These are our features, right? You know by now, right? X1 and X2 are our features. Now, logistic regression is this model, right? So you have, I'll draw very big, relatively big. So this is called neuron in neural network. Neuron or unit, right? What happens is that it takes inputs. Here there are two features, and we also supply one for bias unit, right? And these are weights B, W1, and W. We calculate Z here, which is linear combination. And if you use sigmoid activation, we use that, right? We calculate this. So Z is calculated as Z is equal to B plus W1x1 plus W2x2. Correct? And here we are using sigmoid activation. And you get the output. This is your logistic regression model. In neural network, what we'll do is we'll replicate many such logistic units. Getting it? So this becomes one layer of a neural network. It has got 3 logistic units. So we are stacking logistic units in a layer. Now you can have another layer with some logistic units. So here what I will do is the output of this goes here, goes here, goes here. Right, many logistic units added like this. So this is your neural network. So you can think of neural network as, many logistic units added together. But generally, we do not use sigmoid activation in neural network. Instead of sigmoid, we use activation called as ReLU. I will not talk everything about that today. So ReLU basically does something like this. So ReLU activation, right? So if you have the value of Z like this, any value again between -infinity to +infinity, ReLU assigns value 0 to all negative numbers, and then it just keeps the positive, it returns the positive values. This is your ReLU activation. And researchers found that ReLU activation works well when you try to train deep neural network models. Deep meaning you add many such layers. This is one layer, this second layer, this is one layer, second layer, this is output layer. So if you add more such layers, and here you get Y, right? So you can use neural networks both for classification and regression. So if you want to use it for regression, whatever Z that you get here, you will just output that Z. Use linear activation here. If you want binary classification, you will use a logistic unit here. Just a single change. And you can change it for regression to classification. Now this entire thing is trained end to end. Training becomes complex, but Zeal has given you a key, master key yesterday. You just specify this model, use grad function. You will get all gradients computed automatically. I'll take your question. Okay. This is what will happen. But again, don't worry about this. This is some model, right? This is the model in neural network. What loss will you use for classification? Binary classification? BC loss. Got it? That's it, nothing else. So you have 5 questions. You can ask 5 questions and get it clarified. Yes, your question. So we are taking derivative with respect to weights. So higher order polynomial doesn't matter. Our functions are linear in terms of weights. Feature can be anything. So that's not a problem. Yes. Any other questions? Yes. Good question. The question is weight W1, W2 will be there also for the neurons? No, there will be different weights now. So there is slight, this becomes, let's say, this is W1. I'll give some names to this. So this is W1 of first neuron, of first layer. You have, this will become also W1, but first layer, second neuron. This is W2, first, yeah, this is W2, first layer, second neuron. Getting it? This is W1, first layer, third neuron. W2, first layer, third neuron. This is basically, this is B1, this is B12, 11, B11, B12, B1. These are different weights. So now with the same architecture, we got a very complex model. So this is equivalent to adding higher order polynomials. Intuitively, by adding these layers, we are basically getting the same effect as you will get by adding higher order polynomials. But in case of higher order polynomials, you are computing them yourself. Here, if you are lazy, put neural network. Neural network will do that job for you. You don't have to compute them. Right? You have to just set up the neural network and you will have the same effect as creating higher order polynomials. Getting it? Keep this insight in mind. And now of course, with this, how many features are there? Let's do how many weights are there? Let's do weight counting. 3 per neuron, 3, 3, 3, there are 9. 9 and again 9 here, correct? 9, this is there, they are not 9, more than that actually. 12. 9 plus 12, 21 plus 4, 25. So we have suddenly a function with 25 different parameters. Bias is also counted, right? There is a bias also, right? So that's why there are 4 per neuron here, correct? So there are 3 per neuron here. So this is 3 into 3, which is 9. There are 4 per neuron. So 4 into 3, there are 12. And there are 4 here. So you get 12 plus 9 plus 4. So you suddenly get a function with 25 different parameters, very complex function. So you are likely to overfit if you do not have a lot of data for this. So it's important to throw in regularization here, L1, L2. And there are some other special regularization for neural network. Just that people will talk about. Okay, this will be covered in detail in some other session. So hang on till that. It's not the topic of this session. One more thing that is left, and I don't think we'll have time for that because I want to go through the practical aspect of this, which is computation of this particular part, the partial derivative. I will actually share a note on this partial derivative. I'll share a derivation that you can go through. Okay, so I'll give it to Zeal or I'll put it on Discord. Okay, so yeah. Good question. Thank you. So the question is, how do we set up the regularization rate? A very good question. We do not, we do not include this regularization rate, this lambda. We do not get it through optimization. We need to do something else to do that. Did I talk about hyperparameter tuning yesterday? So let us do that when we do the collab. But let me explain that why. Wait. Okay, so there is an important concept called HPT, hyperparameter tuning. So I'll give you a scheme for this. So we have training data. We divide our training data into 3 parts. A large chunk is train. Second is val. Sometimes people also call this as development set, dev or val set. And third is test set. So test set is something which is not at all exposed. This is something which is hidden from the model. Okay. Validation set is also hidden for some time. So now this is the recipe. 1. Train the model. With train set. That time you will have to set this lambda to some value. Let us say set it to, let's say, 0.1 or something like that. Now comes the fun part, hyperparameter tuning part. Next, what you should be doing is, you should be defining a set of values that you want to try for lambda. So typically what people do is, so we define set of values. So you say 10 raised to minus 4, 10 raised to minus 3, 10 raised to minus 2, 10 raised to minus 1, 0, 0.1, sorry, not 0.1, 0, then 1, 10, right? See, the values are increasing by tens. So we are first doing sparser thing and figuring out which are 2 regions where the lambda is lying, and we can do second hyperparameter tuning. But let's focus on this. So we define these many values. Okay. Now what you do is, for each lambda, train the model. That's the first part. And after training model, what do you get? What do you get after training the model? Yes? Loss, not loss. What is the end result of training the model? Not accuracy. Weights, yes. We get parameters, right? Getting parameters is the end result of the model. So you basically get W. And this is W vector, right? Small case, boldface. W vector. I'm also including, by the way, this W includes B and W. This is bias and other things. So get this model. Now calculate metric on val or dev set. So you have to define a metric. What do we care about? Do we care about precision, recall, F1 score, some metric? Loss itself could be a metric. So you find out the metric, you calculate the metric on the dev set. Getting it? Now here what you will have is, for every value of lambda, you will have the value of the metric. At the end of this step, for every value of lambda, we'll have a value of a metric. So if you are not able to visualize that, let me write it. So we had lambda, right? So we also will have value for metric. So there will be value of metric for each value. For each value of lambda. So there will be value of metric M for 10 raised to minus 4, 10 raised to minus 3, 10 raised to minus 2, all the way up to 100. These are values of lambda that we tried. Correct? And which lambda will you select? The one that has got the best value of the metric. If you're taking loss, you will select the lambda with which results into the least loss. If you are using, let's say, precision, recall, or F1 score, you will try to maximize that. You will find the lambda which maximizes F1 value. Okay? And that is your lambda. This is called as hyperparameter tuning. Thanks for bringing this up. I would have forgotten to add this. Getting it? This is called hyperparameter tuning. Yes. Good question. Cross validation. No, we will. Very nice question actually. How does this work in the context of cross validation? Cross validation, this will be repeated many times because your training set will be different. So that will be even more robust. If you do this with cross validation, that will be even more robust. Right now we are fixing the training set. So we do not know whether this dev is only resulting into these values. So you can also try different dev sets. So there I will just give a quick scheme of that. I'm really impressed with the quality of questions. Thank you. So this is the test set, which we do not use. Separate, sacrosanct. And now this part, let's say these are partitions of equal size, though they don't look like that. Okay. Assume that they are partitions of equal size. Each one have got, let's say, point. So let's say this part is okay. So they are equal. Yeah, they are basically equal partitions. Now let's give them number. This is partition 1, 2, 3, 4, and 5. Now what you will do is you will first define lambda. Again the same thing. 10 raised to minus 4, 10 raised to minus 3, 10 raised to 2, 0.1, 0, 1. By the way, once you identify best lambda and the second best, you can do further fine search within that. Right? Within that range, you can launch even more finer search. But again, remember, this requires you a lot of computation. So you can decide just to stop with this first cut exploration. I'll take your question. Now for each lambda, for each fold. So here fold will be So we'll have folds, right? So we'll have how the cross validation, what sets are there? 1, 2, 3, 4. Training, 5 test. 1, 2, 4, 5 training. 1, 3, 4, 5 training. 2, 3, 4, 5 training. 1 as test. And 1, 2, 3, 5, 4 as test. These are the folds. Getting it? Explicitly writing them. So these are training data, these are tests, this is the validation data or dev data. No. We don't break test data into further pieces. Test data is kept separately. And here, before doing this shuffle, so you can shuffle the data before if there are any orders in the data and other things, and then make folds. Now for each fold, you will train the model. You will get W by training model on fold. Correct? A train model on fold, and we will calculate the value of the matrix metric on val. You will calculate value of the metric on the validation set. Getting it? So now you have how many metric values? 1, 2, 3, 4, 5, 6, 7, 8. 8 into 5. There will be 40 values that you will have. Getting it? Clear?
Yeah, yes, sir. Yes, sir. Yeah.
Clear, no? Is there any question online? Now, there is one more step that is remaining. Once you identify the right value of lambda, so this is an important step. Set lambda to lambda HPT, value that we identify from HPT, and train model on entire data set. Of course, not test. Okay. Train model on the entire set, and that becomes base model. Getting it? What is the difference? Don't get confused. I just use lambda HPT now. Huh? And when you use tools like sklearn, this step is automatically done by sklearn. You don't have to worry about it. They use this best lambda, and then they train the model on the entire data and give you the weights. Clear? By the way, this is very, very important part as far as practical machine learning is concerned. Any questions? Yes. Sorry, will there be? So your question, if I understand it correctly, what you mean to say is that if I use this lambda, if I decide lambda through HPT, will I lose some features? Yeah, if you are using L1 regularization and if lambda that you obtained is high, there will be strong feature selection. A lot of features will be driven down to 0. If lambda is low, for example, with L1, you may not lose a lot of features. So it entirely depends on the value of lambda. No, no, it is not. It is data set dependent. So the question is a specific value of lambda we can use? No, it is totally data set dependent. And this is totally data driven way of selecting that lambda. Right? You have to do it for every data set. But remember, there is a cost involved here, right? See, here we are doing 40 iterations, 40 training iterations we are doing. So sometimes, if you do not have so much of computational budget, people randomly select some values of lambda, coarser values of lambda, and then they'll do hyperparameter tuning with lesser values. So what will happen is that if you are, let's say, less computational budget, so what you will do is you will use, let's say, lambdas like 10 raised to minus 4, 10 raised to minus 2, 0, 10. Now less values of lambda, so lesser training. Once you identify that your good lambda lies in this region, you can have another one where you'll use more fine-grained stuff like this. So if you identify it is in this region, you can have another round where you'll use as to 0.9, 0.8, 0.7, all the way up to 0.1. If you care about that last bit of juice, nothing comes for free. You need to do this work yourself. Okay. Sometimes you have two hyperparameters. So if you have two hyperparameters, what happens is that you have to do grid search. So this is, let's say, lambda, and there is some other hyperparameter, lambda 1 and lambda 2. You can also do both the regularization simultaneously, L1 and L2. So you can have function like BCE plus lambda 1 L1 plus lambda 2 L2. That is also possible. Then you have to search for these two values. So you have basically grid now, right? You have grid. So select some values from here, select some values from here. And evaluate models on these points on the grid. You will select lambda, you will select the values. So if this comes out as the best value, you have corresponding value of L2 and L1. Sorry, value of lambda 2 and lambda 1. Clear? Is there any confusion? Just a minute, I'll take. No. This is called as elastic net regularization. It will have both the effects. Independent of? No, we tune them simultaneously by using a grid. That's why I've created this grid. I'll tune for these values. So this value of lambda 1, lambda 2, this value of lambda 1, lambda 2. So I'm tuning them simultaneously, not tuning them separately. Yes. Yes. Yeah. This is totally the tuning depends on amount of resources that you have, computational resources you have, and what kind of values you expect. Any other questions? Is this part clear? This is, I would say, a very important part as far as practical machine learning is concerned, because you have to do all this. Yes, Karma. Yeah, you can combine with this, and what would happen is that you will get only weights for those 50 features which are important, and rest 50 will be driven down to 0 totally. Yeah, but those 50 features also, no, because we are adding this L2 round, they cannot take very large values. They'll have to take smaller values. So we'll go for a slightly inferior model, but it will be robust model. Now, by adding regularization, we are reducing the quality of the model a bit, right? We will not get low training loss always. We will get slightly higher training loss because we have penalty now. But that is okay. That is on training. But on test data, it is likely to perform well. See, our point is not to do well on training, right? We want to perform well on the test. So the same way, right? Your objective is not to do well on what you learned, but how you apply this, how you generalize this to many problems that you will see in outside world. Okay. Any other questions? All right. This looks good. Okay, we have 20 more minutes. All right. Did I miss anything else? I think this is all. By the way, so one part that I have not covered is the partial derivative, and it will take time. So I will upload the derivation of this in Discord. So go through the derivation. I mean, straightforward, just for the completeness purpose. It will involve concepts from your 12th standard derivative. All right. So now what we'll do is we'll go back to our collab yesterday. But before going to that collab, right, I mean, I'll explain few things. See, I'm not so interested in walking you through the collab, because you can also do that by reading through it. I will give you the philosophy of solving the problem in industry. So typically, we are trying to solve digit classification problem. It's not really digit, but it's specifically we are trying to solve this problem. So first part is you need to get training data. So first step. You might have to work with domain experts to get this and other things. We have talked enough about it yesterday. Second step usually is called data exploration. So you need to, now this data that you get, right? You should do this exploration only on training data. Don't do exploration on test data. Test data is something that you should set aside. Don't do any exploration on test. Otherwise, you'll learn something from test which we will try to apply in training, and the whole point of generalization will get washed away. So keep data, test data aside. You will do visualization. You will visualize, you will explore different features. Have you heard about histograms, bar charts, right? So you can do histograms, you can plot histograms, bar charts. Then there are some other specialized plots that you can plot for every feature. Then you can do correlation analysis between different features to see which features are correlated. Okay, so do that visualization. Then you can also do feature selection, find out which features are important. If you have time, only include those features which are important. Don't use all the features. So for this, you might have to consult with domain experts. You can also come up with important features through your visualization and exploration. Right? Different statistical measures that you will calculate per feature. Based on that, you will decide that some features are not so useful. So you will decide to throw them away, right? So you do feature selection. Now you have final data set. So the first thing that you should be doing is build. So basically, you estimate accuracy or any metric that you care about on training set. With common sense. What is common sense? Common sense, yesterday we saw this dummy classifier in sklearn, right? So in this handwritten digit classification data set, if you see that most of the images are of digit 5, let's say 80% images are of digit 5 and only 20% images come from other digits. So if you get a new image, assuming training and test distribution is the same, if you get a new image, you will label it as, let's say, digit 5, right? If you label everything as digit 5, what is the accuracy you're likely to get on training set? Yes, 80%, because 80% of label are label 5, right? Everything is labeled as label 5. Then 20% is wrong, 80% is accurate. So you have your baseline model has 80% accuracy. So if you build any model which has less than that accuracy, it is not going to be useful. Getting it? All right. So the fourth step now, then you, so here we talked about this. We have already decided this is a classification problem. You also need to figure out what is the right kind of model to use here, right? What is the problem? Is this regression / classification problem? Is it a single label problem or multi-label problem? So all that you need to figure out as part of the exploration initially. Once you figure out that, let's say this is a classification problem, so you should build your first model. Build first model with default parameters. Default parameters of classifier. By the way, these parameters are classifier parameters. So in sklearn, you have, let's say, logistic regression classifier. You simply instantiate logistic regression classifier without any parameters. So by this, what will happen is that all default, we are using logistic regression classifier with default setting. And get the accuracy or get the metric that you care about. And for doing this, right now, from this step onward, you should now have the training set split into two parts, training and dev set, development set. So calculate these metrics on dev set. Or you can do cross validation, that is also fine. You can also apply cross validation strategy. But this is the simplest thing I'm telling you. So calculate metrics only on dev set. And then compare this with the common sense model, what you got. So with this, you will also be able to build story, right? You use common sense model, this is accuracy. You use logistic regression model with default setup, this is accuracy. And here you should also now observe. You should observe learning curve. You should see this is, let's say, training. This is ideal, correct? But instead of this, if this guy is going like this signifies overfitting. If validation accuracy shoots up like this is overfitting. So you should diagnose all these issues, right? Is model getting trained properly? If model is underfitting or overfitting, or if it is training very slowly, then you can also sometimes increase the learning rate. Okay. And then, right, if it is overfitting, what will you do if the model is overfitting? Add more data or penalize the complexity. Good. Good. If the model is underfitting, what will you do? Add more capacity, that is add second order polynomial, third order polynomial. How do you know whether the model is underfitting? High, yes, got it. And in overfitting, first training and test, both of them come down, but after a point, validation loss shoots up. Good, so you should then apply those strategies. Next step is hyperparameter tuning. Once you are happy with these steps, next step is hyperparameter tuning. There are many hyperparameters. Sometimes in the model, you should tune them. So there are two strategies that are there in sklearn. One is called grid search, CV. We saw grid search, right? This is grid search. It literally defines a grid. So if there are 3 hyperparameters, you will have 3D grid, 4D grid, and so on, right? You can see that as you add more hyperparameters, number of points where you have to evaluate it will shoot up. You get that point? So you have to train the model that many times. For each of these points, you have to train a model. And you know, model training on a very large data set will take a long time. So you can, so that is grid search CV. So if you have, let's say, a small number of parameters, and each parameter does not have too many values, go for grid search, right? If you have large number of parameters or even small number of parameters with many values, you can go for randomized search CV. In case of randomized search CV, what happens is that instead of explicitly specifying the parameters, we specify parameters with some distribution. We specify the distribution of the parameters in randomized search CV. Okay, and then the grid is sampled from the distribution that is specified. And here we also specify the budget. We also specify how many checkings we have to do, at how many points we have to do this evaluation. So that's how you can also control your budget, computational budget. Got it? So this is like the first step towards. So there are more sophisticated hyperparameter tuning techniques available. There are hyperparameter tuning services available on cloud platform for neural networks. One of them, one such service from Google is called Wazir. So Wazir is used for hyperparameter tuning in neural networks where there are far many number of hyperparameters. So randomized search CV can be thought of basic Wazir. Okay. So in your collab, I have used this grid search CV, and there we are trying to search for lambda for logistic regression. So you will be able to see that. Then one more point that we have to discuss is, any questions? Then yes, go ahead. You can do that, but people don't do that generally. You can totally do it. Yeah, the question is, can you use optimization techniques for HPT for these hyperparameters? You can do that, but people generally don't do it. They go through this grid search. Grid search is also optimization in some sense, right? We are first defining the space and then doing discrete evaluation in the points. We are visiting discrete points in the space rather than doing continuous optimization. Anyways, any other questions? Great question again. Yeah. Here? Any question? Good. So final part is evaluation, right? So by the way, do you notice that for every hyperparameter, we get a new model? So the number of points that we evaluate on the grid, we have those many models. Correct. So this hyperparameter tuning is also called as model selection. This is very simple model selection that I'm describing, but there are more advanced ways of doing it. Right? It's very simple, my model selection. This is the point that I want to note that each grid will define one model, and this will be a different model. And model is defined by weights, correct? So this model, each of these models will have different weights. So many models we are training. So sometimes people also, they do not throw away these models, but they take average of output from each of the model. You retain all these models. While prediction, you use each of these models, get the output from them, and average out all the outputs. Or take voting style scheme. It is called this. That style of learning is called as ensemble learning. The philosophy is that why should I waste my resources? I've already trained so many models. I'll just use all of them. Because see, all these parameters, it's very funny, right? I mean, all these parameters depends on the training data. And if you're not sure if your training data itself is not constructed properly, if it is noisy, then whatever you're constructing on top of that can be very shaky. So that case, people use this ensemble learning. They take all these different variety of models and try to make use of them for final prediction. Okay, remember all these techniques. I'm just mentioning them in passing, but they'll be described in more detail in subsequent sessions. Now, evaluation, right? So finally, let's say we have one single model. We are happy about it. We'll evaluate it on test set. Right? We always report accuracy of the model on the test set. Remember that. We do not report training accuracy. Accuracies are always reported on the test set. And those accuracies carry some weightage. And based on that, we take further decision whether we want to use this model in some other system, in production, for real life use cases. It totally depends on how it does on unseen data. Getting it? So evaluation, for classification, the evaluation, the basis of evaluation for binary classification is what is called as confusion matrix. Let's say these are two labels and these are predicted labels. If the true label is 0, predicted label is 0, we are happy. This is also a happy state. True 1, predicted 1, no misclassification. These are problem cases. True is 0, predicted as 1, problem. True 1, predicted as 0, problem. Right? So now there are specific names that we give to each of these cells. So this cell is called TP, which is true positive. Assuming 1 is the positive class, true positive. This cell is true negative, TN. Actually is 1, but predicted is 0. So this is falsely predicted as negative, FN. I remember it that way, otherwise it's very confusing. It's falsely predicted as negative, right? This is predicted as negative, but this is false, so it is FN. And this is falsely predicted as positive. That's why FP. Keep this in mind, otherwise we get confused whether this is FP or this is FP. Yeah, I don't even remember what is type 1, type 2. Yeah, got it? So remember this, huh? And based on this is confusion matrix. And now based on this, we calculate different metrics. One of them is called accuracy. Accuracy is easy, right? TP plus TN divided by everything, all summation of all FP plus the sum of all these. So accuracy is not a good metric, typically. If you have imbalanced data set, one class has disproportionately large number of examples, other has less number of examples, accuracy can be misleading. So we have better measures. One is called precision. And precision is the ratio of true positives plus false positives. Right? So what percentage of positives are true positives? These are total positives, right? These are total predicted positives. TP plus FP are predicted as 1. So these are predicted positives. So this column, right? This column is predicted positives. And this column are actual positives. This row, so this row is actual positives. This column is predicted positive. So precision is calculated on predictive positives. So the way again remember is this is predicted positives. So there is pre. Otherwise it's very hard. I mean, we get confused all the time. Precision on predicted positive. And you have another measure called recall, which is calculated on actual positives, which is TP by TP plus N. Okay, we are already off time. I did not realize. And then we call what is called as F1 score, which is harmonic mean of precision recall. I think this is precision into recall divided by precision plus recall, I guess. I may be wrong in this. This we need to double check this. So these are the measures we calculate. Double check this measure. I'm not sure. I might have goofed up. So we calculate these measures, we report them. And if these measures are okay, then people decide to use the model. Now question is, this model, after running it for some days, you might start getting data with different distribution. You need to keep monitoring the accuracy of the model. If it falls, then you need to retrain the model. That's how people operate in industry. Anyways, we are way over time. Thank you very much. It was fun talking to all of you, and wish you good luck for the summer school and your career as data scientist. Take care. Thank you. Thank you.
Thank you, sir.
Yeah, we don't have any time for questions. We can discuss on Discord if you have any questions. That's the channel. Let's make use of that. All right. Thank you.